If we may get started, please. It's my pleasure this afternoon to introduce Professor Roger Revelle, Professor of Science and Public Policy, University of California, San Diego. Roger is a former director of the Scripps Institute of Oceanography, 14 years, science advisor to the Secretary of the Interior. He's a member of the National Academy of Sciences, and he's contributed in the international area, for example, being a part of the U.S. delegation to the United Nations Conference on Science and Technology for Development. His recent articles appear in journals such as Energy and Climate, Science, Scientific American. They've treated topics, for example, global population and aspects of food problems, the carbon cycle, and the biosphere, energy use in rural India, ocean drilling, and assistance a climatologist can lend to developing countries. We're looking forward, and I'm looking forward to his talk on the role of the oceans in Earth's climate and carbon budget. Professor Revelle.
I'm going to talk mostly today about the carbon dioxide problem, which is a subject of considerable interest to at least one component of this laboratory. It's possible to say, I think, that from the standpoint of living creatures on this planet, and particularly, of course, from the standpoint of human beings, that the most important substance there is, the most important chemical compound there is carbon dioxide. And that's true for three reasons. In the first place, we're all made of carbon and a few other things, and all of that carbon comes to us by way of plants, which in turn extract carbon from the carbon dioxide in the air and combine it with water to form sugars and other related substances. So life as we know it, or as we can even imagine it, would be impossible without carbon dioxide. Second, from the standpoint of us animals, as opposed to plants, an essential substance for us is free oxygen. Oxygen to facilitate our very high level of metabolism. You ever stop to think about a tree and why a tree is so sedentary? It's because a tree has so little energy. A tree that tried to walk around would quickly collapse from lack of energy. We're among the most energy using of all animals. In fact, 1 kilogram of human flesh radiates about 10,000 times as much energy per second as an equal kilogram of the sun. And this very high level of energy use depends upon the oxidation of organic matter in our metabolic systems, and that oxygen, which is essential for our high metabolism, probably all come from the reduction of carbon by plant photosynthesis, reduction of carbon dioxide by plant photosynthesis, and the freeing of oxygen. Third, another essential requirement for living creatures is the presence of liquid water. As far as we know, we're the only planet in our solar system that possesses liquid water on its surface. And part of the reason for this, of course, is that we're just about at the right distance from the sun. But an equally important reason is that the presence of carbon dioxide in the atmosphere produces something which has been called the greenhouse effect. Because the carbon dioxide absorbs infrared radiation, that scatters it back to the lower atmosphere. The temperature near the Earth's surface is about 30 degrees centigrade higher than it would be in the absence of carbon dioxide. A 30-degree drop in the surface temperature of the Earth would mean that the entire Earth was covered with ice and that there wouldn't be any liquid water on it. So the carbon dioxide plays three essential roles, more than essential, fundamental roles in our very existence. At the same time, we're now talking about something called the carbon dioxide problem. And what I want to do today is to talk about this carbon dioxide problem. We can define it not perhaps in a word or a sentence, but in a paragraph. Very accurate, continuous measurements of the carbon dioxide content in the air at two isolated stations. In Mauna Loa in the Hawaiian Islands, on the top of Mauna Loa in the Hawaiian Islands, and at the South Pole, have been made. These measurements have been made since about 1957, something over 20 years. And they show beyond any doubt that the carbon dioxide content of the air has increased by about 60% during the past 20 years, and that the rate of increase is accelerating. It is equally clear that human activities, the burning of coal, oil, and natural gas, and the clearing of forests for agricultural and other purposes, are the major sources of the added carbon dioxide. If the worldwide economy, with its insatiable demand for energy, continues to grow and fossil fuels continue to be the principal source of energy, the carbon dioxide content of the air can be expected to double before the year 2050, excuse me. That is within the lifetimes of many human beings who are now alive. Because carbon dioxide in the atmosphere absorbs and re-radiates infrared radiation, the temperature of the lower atmosphere will rise perhaps to a greater extent than at any time since the end of the last ice age, about 10,000 years ago. Profound changes in the world climate might occur, with correspondingly great impacts on human societies, and the effects are likely to persist for many centuries thereafter. Once we've embarked on this path of increasing carbon dioxide and its possible accompanying climatic changes, these climatic changes will persist certainly for 500 years and perhaps for a longer time. This is the carbon dioxide problem. This problem is virtually unique among today's human-induced problems. Heaven knows we have enough of them. But this is a unique problem in three ways. Not entirely unique, somewhat unique. First, its long time scale. Second, its uncertainty. And third, its planetary character. Like the movement of a glacier, which is barely detectable from year to year, but has very great cumulative effects over many years, the effects of the annual increase in atmospheric carbon dioxide are imperceptibly small. We're none of us aware of it in any physiological way. And in fact, the effects in terms of climate change, potential climate change, have so far been imperceptible compared with the noise level. The carbon dioxide signal is below the noise level of interannual fluctuations in climate. But the effects are likely to be cumulative from year to year, and in the long run, they're likely to prove both large and inexorable. Human societies have no memory of a comparable climatic event in their recorded histories. Although the coming and going of the last ice age was an event of even larger magnitude, its memory is submerged far below consciousness among today's human beings. We may still have some kind of a racial memory of the last ice age, but it doesn't manifest itself in any at the surface of consciousness. Uncertainty is the second fundamental characteristic of the carbon dioxide problem. And before I talk about these uncertainties, let me first say a word about the certainties. I mentioned, to begin with, the measurements that have been made on the top of Mauna Loa and at the South Pole. And I'll try to draw these on the board. If this is CO2 in the air, and this is time, and let's suppose we start at 1957 when the measurements began, and go up to 1977, which is the last year for which we have well-analyzed data. The measurements were made by a rather fancy infrared analyzer that took the measured the infrared absorption in continuous air samples. So the measurements were made by a continuously recording device. And what they show was that you have a carbon dioxide content in the air at the top of Mauna Loa that looks like this. And if we draw a curve through this, it should, if I'd drawn this correctly, it would be an exponential curve. Slightly curving upward. These fluctuations, which are on both sides of the average of the curve, are annual fluctuations, and they depend upon the fact that in the summertime in the northern hemisphere, there's a good deal of photosynthesis, which withdraws carbon dioxide from the air. In the wintertime in the northern hemisphere, there's a good deal more respiration than there is photosynthesis, and carbon dioxide is released to the air. So these seasonal fluctuations in the carbon dioxide are about 3 parts per million. If this is, let's say, 300 parts per million, and up here it's 330. Well, let's say this is about 3. This is a little bit more than 300. This is about 310, and this is about 330. These annual fluctuations are about 3 parts per million. And that's, as I said, due to the seasonal differences between photosynthesis and respiration. We find exactly the same kind of curve at the South Pole, but with the annual variations being less and a lag of about 2 years in the total amount in the air compared to the measurements at Mauna Loa. These are both quite understandable. First place in the southern hemisphere, there's much less photosynthesis because the southern hemisphere is mostly ocean, and also correspondingly much less respiration. But more particularly, the lag is due to the fact that the carbon dioxide, the added carbon dioxide, is coming primarily from human activities in the northern hemisphere where the lands are concentrated. And there's a window, or sort of a wall or barrier at the equator across which the atmosphere doesn't exchange very rapidly or very readily. And so that it takes about 2 years for the South Pole station to catch up with the Mauna Loa station. The accuracy of these measurements is about 1/10 of a part per million. And if we look at this curve here in some detail, it shows wiggles. I didn't draw the wiggles, but it's not an absolutely straight line. Sometimes there's somewhat higher increase in the atmosphere, and sometimes a somewhat lower increase, but overall a continuous increase. That's the only certainty in this morass of uncertainties. that I want to talk about today. However, quite a while ago, the great Swedish chemist Svante Arrhenius and the American geologist Thomas C. Chamberlain in the 1890s said that postulated that the burning of coal, by the growing rate at which coal was being burnt by the expanding and developing industrial civilization, would very likely increase the CO2 content of the air, and that this in turn could have an effect on climate in raising the temperature of the lower air. A man named Callender, about 1940, said that the observed increase in temperature, global average temperatures over the Earth, and particularly in the northern hemisphere, which had been going on from 1870. For about 70 years, the global temperature in the northern hemisphere increased, slowly but more or less steadily. And Callender said this could very well be due to the carbon dioxide, the added carbon dioxide in the air. The measurements made, however, in the 1890s, and even the measurements made in the 1930s and early 1940s, were not very accurate. They had probably the 19th century measurements might be in error by as much as 10 or 20 parts per million. The measurements even in the 1930s, early 1940s, probably were in error by a few parts per million. It wasn't until the development of the infrared analyzer in the late 1940s and early 1950s that very accurate measurements could be made. And these are the measurements that have been made at Mauna Loa and at the South Pole by a great chemical analyst, Charles David Keeling. You said I was going to talk about the ocean, Dr. Batesel. I will talk about the Scripps Institution of Oceanography in the sense that Dr. Keeling was brought to Scripps in 1957 to do that, to make these measurements as part of the International Geophysical Year. And he's been making them ever since, and he's still at Scripps. So that's at least one way in which the ocean affects the carbon dioxide problem. He wants to measure carbon dioxide in his belly. He never really wanted to do anything else. He measures it with extreme accuracy and extreme precision and thinks about all the things that might possibly go wrong with all the measurements related to carbon dioxide. Really a remarkable individual. And he's produced this remarkable result, this analytical result. And a great pyramid of speculation and uncertainty has been built upon this result. For example, we know that since, say, 1850, about 130 years ago, there were probably around 130 billion tons of carbon released by the burning of coal, oil, and natural gas. And that, of course, resulted in the production of carbon dioxide and water. Nothing particularly notable about the water, but the carbon dioxide produced by this combustion of coal, oil, and natural gas was until fairly recently thought to be the principal source of the added CO2 in the air. And if we compute on the basis of Keeling's measurements between 1957 and 1977, what proportion of the added carbon dioxide produced by fossil fuel combustion stayed in the air and was found at Mauna Loa, it's of the order of perhaps 50%, about half of or perhaps a little bit more than half of the added carbon dioxide has stayed in the air. And here we come against one of the first of our uncertainties. We don't really know what the carbon dioxide content was in the middle of the 19th century. So we don't know before 1957 what fraction of the CO2 produced by the burning of fossil fuels remained in the air. There's a man named Binzi Stoiver at the University of Washington who, by measurements of carbon-13, carbon-12 isotope ratios, has concluded that, in fact, the CO2 content at that time was considerably lower than it was usually assumed to be. In other words, more has been added, or more CO2 has been added than you would compute on the basis of Keeling's measurements. And this has raised the problem of where does the additional CO2 come from? And most biologists, and at least most American biologists, are convinced that forests are being cut down at a rate greater than they're growing in the world as a whole. And that this is, and I myself am convinced that this has been true ever since 1850, and that the combustion of wood, the combustion of the wood stored in the forest and of the reduction of the organic matter in the forest soils, or the oxidation of the organic matter in the forest soils, that these have both contributed perhaps as much as as much carbon dioxide as the fossil fuel combustion has contributed. We then are faced with an even more serious problem. Where is the carbon dioxide content gone? Where is the added carbon gone, carbon dioxide gone? And there are two schools of thought about this. One of them is that it's going right back into the biosphere. That is, carbon dioxide added to the air should result in an increase in photosynthesis. It acts just like a fertilizer, just as nitrogen or phosphate does, and it's just as essential for plant growth as water. So it could very well be that photosynthesis has increased in the uncut forests, which means that the trees are getting bigger. That would seem like a very simple thing to find out about if the trees are getting bigger. The trouble is that where the trees are getting bigger is probably mostly in the tropical rainforests, and the trees in the tropical rainforests have no tree rings because there's no difference between summer and winter. The result is that it's essentially impossible to tell whether the trees are bigger or not. The alternative explanation or the alternative hypothesis as to where the carbon dioxide has gone is that the oceanographers are wrong about the amount that's gone into the ocean, and that much more has gone into the ocean than they think has been the case. Naturally, I take a dim view of this second hypothesis, and for fairly good reasons, I think that the biosphere has not been either much of a source or much of a sink for carbon dioxide. But these questions about where the carbon dioxide has come from and where it's gone, how much will be how much of that produced has remained in the air, are of course a first order uncertainty, because if we're going to predict how much future CO2 will be in the air, we have to have some notion of how much stays there out of the total amount produced. There is, however, an even more fundamental uncertainty, and that is how much will be produced. During the past 125 years, the rate of combustion of fossil fuels has gone up about 4% a year, exponentially, with a doubling time of around 20 years. As long as that doubling time of 20 years persists, everybody will agree, one of the things that's not quite as uncertain, everybody will agree that more and more carbon dioxide will remain in the air. There's a larger and larger proportion or fraction of that produced will remain in the air. But there's no reason whatever to believe that we're going to continue using fossil fuels at 4% a year, and with an increasing use rate of 4% a year, an exponentially increasing use rate. It's just as likely that, in fact, we may have reached the peak of fossil fuel use. That is, that because of the disappearance of cheap oil the appearance of very expensive energy, that the energy uses may decline markedly. And that would be particularly true if we have a worldwide depression and a large amount of unemployment and human misery. The carbon dioxide problem would then be substituted for by a ghastly, hair-curling economic depression. It's possible that there will be some intermediate between no increasing use of fossil fuels and the 4% increase. The lower the rate of use of fossil fuels, the longer the time will be before we double or quadruple the carbon dioxide content of the air. The doubling or quadrupling, nevertheless, would be inexorable and inevitable if use rates continue at, say, even 2%. Growth of fossil fuels continues at even 2% a year. The third major kind of uncertainty is what will be the effect of the additional CO2 in the air. Supposing we double carbon dioxide content, what will be the effect on the climate? The best, in my opinion, the best estimates of these effects have been made by Siakuro Manabe and his colleagues at the Geophysical Fluid Dynamics Laboratory at Princeton, New Jersey, a NOAA laboratory. Manabe thinks that with a doubling of the carbon dioxide content, that the global average temperature will rise about 2 degrees centigrade. The temperature at, say, in the northern tier of states in the United States will rise about 5 degrees centigrade, the yearly average temperature. The temperature at, let's say, in Alaska and northern Canada would rise 7 or 8 degrees centigrade. These are changes in temperature, as I said to begin with, larger than any we've experienced. Excursions in average global or regional temperature, larger than any that have been experienced for the last 10,000 years. Perhaps even more serious would be that these changes that these latitudinal differences in the temperature increase would result also in a profound change in the regional patterns of precipitation. Some regions would become much drier, some would become much wetter. And which regions would become drier and which would become wetter, I believe is still almost a completely unknown problem. The climatic effects increase more or less as the logarithm of the CO2 content of the air, so a quadrupling of CO2 would not result in another doubling of temperature or another 2 degrees increase in temperature, but a somewhat smaller increase than that. Nevertheless, this quadrupling is very likely to occur by the end of the next century, and with even larger climatic effects than those that I have specified. It's only fair to say that there's very considerable uncertainty about these climatic models. The uncertainties arise from two principal causes. One of them is that it's possible that the cloudiness of the Earth would increase, and that the clouds would increase in such a way that the albedo, that is the reflectivity of the Earth's surface, would increase. If we have low clouds over a larger area of the Earth than we have now, then that certainly would be very likely, that would be almost surely the outcome. The reflectivity of the Earth would increase, less solar radiation would be absorbed in the surface or in the ocean and at the ground, more would be reflected to outer space. And this would certainly be a negative feedback which would reduce the climate effect. If, on the other hand, the clouds are high clouds, just the reverse would occur, because the high clouds have such a relatively low temperature that the radiation from them is lower, the infrared radiation from them is lower than that near the Earth's surface, and that in effect would tend to warm the lower atmosphere and add to the carbon dioxide effect. So we don't really know whether the clouds will be good or bad, whether they'll be a negative or a positive feedback. The one thing that does seem certain is that there will be more evaporation, therefore the relative humidity of the atmosphere will remain constant. If the relative humidity of the atmosphere remains constant, the absolute humidity will increase, which means that precipitation overall, the global precipitation, will also increase. We don't know what will happen to the sea ice in the northern latitudes, and particularly Manabe's calculation indicates that the Arctic ice would disappear in the summertime, the sea ice covering the Arctic Ocean with undoubtedly profound but not at all understood effects on the global climate, basically because of the very great change in the regime of heat exchange between the Arctic Ocean and the atmosphere if there's no blanket of ice insulating the ocean from the atmosphere. The other great uncertainty in the models is that the models at the present time don't take the ocean into account in any realistic way. The atmospheric modelers have invented two kinds of oceans. In one kind, they treat the ocean as if it were a swamp, which means that it has no heat capacity, but is a source of water to the atmosphere. Water exchange is not at all impeded. The other kind of ocean is an ocean covered with a copper plate. In other words, an ocean with an infinite heat capacity, so that the temperature of the ocean cannot change no matter what happens to the atmosphere. Neither the copper plate ocean nor the swamp ocean give at all a realistic picture of the nature of the great atmospheric ocean climate machine. And just to give you a case in point, about a year ago we heard rather widely spread rumors that the British Meteorological Office had made calculations, have a big climatic model, and they had made calculations that showed that the carbon dioxide effect would be negligibly small. But turned out when we got to the World Climate Conference in Geneva, and John Mason, the director of that office, who was a typical Englishman, always tends to play down any natural phenomenon that might disturb the British Raj, had to confess that their model, which they used to demonstrate that there would be no effect, in fact, they'd kept the temperature of the ocean constant, which means, of course, there could not be any effect. And when they had varied the temperature of the ocean, when they'd raised it 2 degrees, then they got the same results that Manabe got. So this was a punctured balloon as far as the climate modelers are concerned. The other uncertainty, not apart from the uncertainty in the models, is the uncertainty as to what will be the pattern of precipitation. There's some evidence from the so-called climatic optimum of the end of the, which occurred right at the end of the Ice Age, when the temperature was perhaps 1 or 2 degrees warmer than it is now, that North America would have a considerable decrease in precipitation, and that other areas, for example, the Sahelian area of the Sahara, would have a considerable increase, just based upon where the precipitation seems to have occurred toward the end, at the time of the climatic optimum. But that climatic optimum may or may not have been a warming of the atmosphere due to added carbon dioxide in the air. It might have been due to some other cause. So we can't really take those fragmentary and uncertain results too seriously. The third or fourth area of uncertainty is what will be the effects. And I want to talk about some of the effects and the uncertainties regarding them. That is, primarily what will be the effects on things about our environment which are of interest to, which are of direct and one might almost say vital interest to human beings. And let me start with the ocean. The ocean, and here I would like to combine both the ocean and the ice, the cryosphere, the ocean hydrosphere and the cryosphere. One of the obvious consequences of the changes in temperature that I've described is that there would be less temperature difference between low latitudes and high latitudes. That is, the high latitudes would be relatively much warmer than compared to their present average temperatures than the low latitudes. So there would be a smaller temperature gradient, presumably therefore much less heat transport between low latitudes and high latitudes, therefore much less wind, because what drives the winds, what drives the atmospheric and oceanic circulations is the transport of heat from low latitudes to high latitudes. Less heat transport, presumably less circulation. If the winds in the atmosphere are lower, then the wind stress on the sea surface would be smaller. And in fact, the wind stress varies as the square of the wind of the wind strength. And therefore, we presumably would have less stirring in the ocean, less weaker currents, therefore less vertical as well as horizontal motions in the sea, and specifically probably a considerably smaller upwelling. And upwelling of various kinds is the principal source of the world's fisheries. So this might have a devastating effect, or at least a serious effect, on the world's fisheries. I've already mentioned the possibility that the Arctic ice might disappear, but might essentially melt in the summertime. A prospect that frightens the glaciologists is that the West Antarctic ice cap would melt, or not would melt, but would melt, and I'm happy to report to you that there are just about as many glaciologists who think that the ice cap won't disappear as there are who think it will. And so you can pay your money and take your choice. Increase more or less as the logarithm of the CO2 content of the air, so a quadrupling of CO2 would not result in another doubling of temperature, or another 2 degrees increase in temperature, but a somewhat smaller increase than that. Nevertheless, this quadrupling is very likely to occur by the end of the next century, and with even larger climatic effects than those that I have specified. It's only fair to say that there's very considerable uncertainty about these climatic models. The uncertainties arise from two principal causes. One of them is that it's possible that the cloudiness of the Earth would increase, and that the clouds would increase in such a way that the albedo, that is the reflectivity of the Earth's surface, would increase. If we have low clouds over a larger area of the Earth than we have now, then that certainly would be very likely, that would be almost surely the outcome. The reflectivity of the Earth would increase, less solar radiation would be absorbed in the surface or in the ocean and at the ground, more would be reflected to outer space. And this would certainly be a negative feedback which would reduce the climate effect. If, on the other hand, the clouds are high clouds, just the reverse would occur, because the high clouds have such a relatively low temperature that the radiation from them is lower, the infrared radiation from them is lower than that near the Earth's surface, and that in effect would tend to warm the lower atmosphere and add to the carbon dioxide effect. So we don't really know whether the clouds will be good or bad, whether they'll be a negative or a positive feedback. The one thing that does seem certain is that there will be more evaporation, therefore the relative humidity of the atmosphere will remain constant, if the relative humidity of the atmosphere remains constant, the absolute humidity will increase, which means that precipitation overall, the global precipitation, will also increase. We don't know what will happen to the sea ice in the northern latitudes, and particularly Manabe's calculation indicates that the Arctic ice would disappear in the summertime, the sea ice covering the Arctic Ocean with undoubtedly profound but not at all understood effects on the global climate, basically because of the very great change in the regime of heat exchange between the Arctic Ocean and the atmosphere if there's no blanket of ice insulating the ocean from the atmosphere. The other great uncertainty in the models is that the models at the present time don't take the ocean into account in any realistic way. The atmospheric modelers have invented two kinds of oceans. In one kind, they treat the ocean as if it were a swamp, which means that it has no heat capacity, but is a source of water to the atmosphere. Water exchange is not at all impeded. The other kind of ocean is an ocean covered with a copper plate. In other words, an ocean with an infinite heat capacity, so that the temperature of the ocean cannot change no matter what happens to the atmosphere. Neither the copper plate ocean nor the swamp ocean give at all a realistic picture of the nature of the great atmospheric ocean climate machine. And just to give you a case in point, about a year ago we heard rather widely spread rumors that the British Meteorological Office had made calculations, have a big climatic model, and they had made calculations that showed that the carbon dioxide effect would be negligibly small. But turned out when we got to the World Climate Conference in Geneva, and John Mason, the director of that office, who is a typical Englishman, always tends to play down any natural phenomenon that might disturb the British Raj, had to confess that their model, which they used to demonstrate that there would be no effect, in fact, they'd kept the temperature of the ocean constant, which means, of course, there could not be any effect. And when they had varied the temperature of the ocean, when they'd raised it 2 degrees, then they got the same results that Manabe got. So this was a punctured balloon as far as the climate modelers are concerned. The other uncertainty, not apart from the uncertainty in the models, is the uncertainty as to what will be the pattern of precipitation. There's some evidence from the so-called climatic optimum of the end of which occurred right at the end of the Ice Age, when the temperature was perhaps 1 or 2 degrees warmer than it is now, that North America would have a considerable decrease in precipitation, and that other areas, for example, the Sahelian area of the Sahara, would have a considerable increase, just based upon where the precipitation seems to have occurred toward the end, at the time of the climatic optimum. But that climatic optimum may or may not have been a warming of the atmosphere due to the added carbon dioxide in the air. It might have been due to some other cause. So we can't really take those fragmentary and uncertain results too seriously. The third or fourth area of uncertainty is what will be the effects. And I want to talk about some of the effects and the uncertainties regarding them. That is, primarily what will be the effects on things about our environment which are of interest which are of direct and one might almost say vital interest to human beings. And let me start with the ocean. the ocean, and here I would like to combine both the ocean and the ice, the cryosphere, the ocean hydrosphere and the cryosphere. One of the obvious consequences of the changes in temperature that I've described is that there would be less temperature difference between low latitudes and high latitudes. That is, the high latitudes would be relatively much warmer than compared to their present average temperatures than the low latitudes. So there would be a smaller temperature gradient, presumably therefore much less heat transport between low latitudes and high latitudes, therefore much less wind, because what drives the winds, what drives the atmospheric and oceanic circulations is the transport of heat from low latitudes to high latitudes. Less heat transport, presumably less circulation. If the winds in the atmosphere are lower, then the wind stress on the sea surface would be smaller. And in fact, the wind stress varies as the square of the wind of the wind strength. And therefore, we presumably would have less stirring in the ocean, less weaker currents, therefore less vertical as well as horizontal motions in the sea, and specifically probably a considerably smaller upwelling. An upwelling of various kinds is the principal source of the world's fisheries. So this might have a devastating effect, or at least a serious effect, on the world's fisheries. I've already mentioned the possibility that the Arctic ice might disappear, but might essentially melt in the summertime. A prospect that frightens the glaciologists is that the West Antarctic ice cap would melt, or not would melt, but would disappear. We had a conference on this subject just last week in Maine, where people came from all over the world, and I'm happy to report to you that there are just about as many glaciologists who think that the ice cap won't disappear as there are who think it will. And so you can pay your money and take your choice. However, it's possible that we can find out more about this, and what their principal task, in fact, was to invent a research program that would tell us more about what the Antarctic ice cap might do. The problem is basically this, that the West Antarctic ice cap is resting on seawater, not on solid ground. Its bottom is parts of its bottom are way below sea level. It seems to be held in place by the ice shelves that surround it, which essentially hold it back. The ice shelves, in turn, are kept from melting by sea ice, by the Antarctic sea ice, which extends out a considerable distance beyond the shelf. If the temperature in the Antarctic latitudes increases by 5 to 10 degrees, one might suppose that the sea ice would melt, the ice shelf would disappear, and the ice cap, the West Antarctic ice cap, would grind into the ocean. Nothing would be holding it back. If this happened, the sea level would rise about 6 meters, about 20 feet. And this might happen in 100 years. And the reason why the alarmists think of this time constant is that apparently exactly this kind of thing happened in Hudson's Bay at the end of the last ice age. That the ice cap covering Hudson's Bay seems to have disappeared in a matter of a few decades. I have no opinion about this. I would point out, however, that it isn't, that even this project, although it's clearly uncomfortable, not quite as serious as it looks. Cities are rebuilt about once every 50 years. I mean, if you look at the number of old buildings in New York, there are perhaps 1 out of 100 that are more than 50 years old, or maybe 1 out of 50. And what we do simply is build New York somewhere else. And similarly with Miami and with London and possibly with Oakland. Might not be such a bad thing. If we look at the effect on the land, we can think of the effects here in different directions. First, the effect on what we have called the unmanaged biosphere, that is the grasslands, the forests, the tundra, the savannas, the rainforests in the tropics, the boreal forests, and so forth. And this is a very complicated problem, and let me now return to what I said earlier, and that is that adding carbon dioxide to the atmosphere will increase photosynthesis. CO2 acts as a fertilizer. And it may very well be that in some places and at some times and with some plants that carbon dioxide in the air is the limiting factor for their growth. If that is the case, then an increase in carbon dioxide will cause those plants to photosynthesize more rapidly. So if you just think about this all by itself, you might think that this would be on the whole, a net benefit to the plants and to everybody, all other forms of life that depend on the plants. Unfortunately, the problem is not quite so simple. It's not quite so simple because of four kinds of problems. The first problem is that an increase in atmospheric temperature accompanying the rise in carbon dioxide would cause an increase in respiration, and it's by no means clear whether oxidation of organic matter, the reverse of photosynthesis, would not proceed at a more rapid rate than the increase in photosynthesis. In other words, we might have a negative effect because of the increase in respiration. The second problem is that an increase in temperature would, of course, cause a disequilibrium in the plants. They would tend to move north into more northern latitudes. Say the spruce would tend to migrate 200 or 300 miles farther north, the center of the spruce population, or the pine population, or the population of any particular species of trees. If this happens, then something called phenology comes into effect. Plants are very sensitive to the length of the day. They're often said to be photosensitive. And plants flower, they drop their leaves, they do everything, and time it by day length. If they move to a different latitude, the day length will be different. It'll be longer in the summer and shorter in the winter than the day length that they're used to. And that is very likely to seriously disturb their behavior. Some plants will be disturbed more than others. So those plants that are least disturbed will prosper. Those plants that are most disturbed will fall by the wayside. So you change the character of the forest. You change the ecologic makeup of the grasslands and of the forests and of the other areas. Fourth, we tend to think of plants as sort of amorphous blobs of organic matter. That is, we think of a tree as capable of growing much bigger than it is, or a bush being bigger or littler, depending upon its environment. The biologists don't think this is so. They think that, in fact, plants have a proper size and a proper shape, just like we do. If you got twice as much food, you might get fatter, but you wouldn't get any taller, and you might not even get any fatter. We all have a proper size and shape. And insofar as plants have also a proper size and shape, then they will not respond they may respond in quite different ways than one can predict to a change in atmospheric carbon dioxide. And it's the combination of the change in atmospheric carbon dioxide and the change in temperature, and therefore in the latitude for different plants, that makes that fraughts this question of the reaction of the natural biosphere, or freights it, whatever the present tense of fraught is. that freights the question of the carbon dioxide in the natural biosphere with great uncertainty. As far as the managed biosphere is concerned, there we have a quite different situation. The United States agriculturalists are quite convinced that they can cope with anything. Particularly the research, the state research workers at the state experiment stations. And they point out with considerable justification that they have in fact coped with a lot over the past 50 years or so as they've learned more about the genetics and physiology of crop plants. Whether they can cope with a problem of the following kind is not quite obvious. At the present time, the greatest food-producing area in the world is the Corn Belt of Illinois, Iowa, Missouri, and Indiana. Here, God seems to have been, as he has in so many ways, extraordinarily kind to the United States. The corn, the climate there, the temperature, the rainfall, the soil is rich and deep, the rainfall is abundant, and the temperature is warm but not too warm, in such a way that the yields of corn have continually increased till they're now about something like 3 or 4 tons, about 4 tons per acre per year, average yields. Very, very high yields indeed. About 10 tons per hectare of corn, about 30 tons per hectare of organic matter. Now, supposing we have a marked increase in temperature and a marked decrease in rainfall in the Corn Belt, it might be necessary to move the Corn Belt into Canada, or at least further north in the United States into Michigan and Minnesota, northern Wisconsin. The problem here is that the soils there are poor. They're podzoles, they're forest soils, have nowhere near the fertility or the adaptability that the soils of Iowa and Illinois and Missouri and Indiana have. So this might result in a very considerable decrease in production in corn production just by having to move the Corn Belt. And it may be impossible to genetically modify the corn plants so they will still yield produce the very high yields in the areas where they now grow. If we think about agriculture as far as the rest of the world is concerned, it's probably true that all the developed countries will be in the same condition as the United States. That is, that they will be able to cope or adapt to a climatic change and take advantage of the change of the additional carbon dioxide. For example, if the experiments in greenhouses are correct and photosynthesis does increase very considerably with added carbon dioxide, and if genetic modifications can be made so that the plants will not respire any more rapidly with higher temperature, then you should get more crops. But we're not really interested in larger crops. What we're interested in is more grain, more wheat or corn or potatoes, whatever, the edible part of the crops. And what must be done, and what I'm sure can be done, and what the agricultural people in the United States are convinced can be done, is to tinker with the genetics of the crop plants. So in fact, the added photosynthesis, production of photosynthetic product or material gets into the seed, and you increase the seed content of the plants, which is what we eat and what we want. If we look at the rest of the world, however, the underdeveloped countries where 90% of all the people are going to be living by the end of this century, the position is very much more grim. It will be more grim for those areas where the rainfall becomes less. It may become better for those areas where the rainfall which become wetter, have a more uniform and constant rainfall. Now, please take note of this word constant. One of the things that we don't know at all, and which the climate models don't tell us, is what will be the variability in climate from year to year. If that variability increases, then the position of the farmers who depend on rainfall, as most farmers in the world do, will become really very bad indeed. And it will become bad because they live from hand to mouth. They live a pretty close to a subsistence existence. They have no reserves. So it doesn't matter how many good years they have. If they have one bad year, they starve to death. So a really bad years coming even far apart might be of might be of catastrophic significance to farmers in the poor countries. It's also probably true that if areas that become drier, which are already more or less dry, if they become drier, the only hope for people in these countries will be immigration. We're seeing already great movements of immigration in different parts of the world. Mexicans and Latin Americans coming into the United States, probably more than 1 million a year. Vietnamese and Cambodians and Ethiopians and people from Chad and from Upper Volta, people from many parts of the less developed world being driven by hunger or by persecution far from their own countries. That these migrations might be, which are so serious now, might be greatly worsened if the climate changes for the worse in terms of rainfall over large parts of the areas of the less developed countries. A case in point being China. China is just barely able to feed itself now. They have so little arable land and so many people that they're on the edge of about half the time of having to import considerable amounts of food grains. If the Chinese climate worsens, if it becomes drier, as is very likely to happen, then the food situation for that quarter of mankind might be greatly worsened. We have, of course, even greater uncertainties when we think about the society's reactions and the political and economic repercussions of such drastic climatic change. And I don't want to say anything about those because I don't understand them very well, nor do I think nor do I know of anybody else who has a clear-cut picture. But what can be done is to think about how one could find out about social reactions and about political reactions and about what can be done on a worldwide basis. Because one of the truly remarkable characteristics of this CO2 problem is that it is planetary. All nations and all peoples on Earth will be affected by the gross climatic changes that are likely to result from a large increase in the CO2 content of the atmosphere. But as I've already pointed out, the effects will not be the same. Some regions and some nations will gain more benefit than harm from an atmospheric CO2 buildup, while the reverse will be true of others. These geographical and national differences will greatly exacerbate the difficulties of arriving at an international consensus on such preventive measures as a sharp worldwide reduction in the consumption of fossil fuels. For example, it's very likely that while we might be seriously damaged in the United States by a drying up of the central and eastern parts of our country, the Soviet Union might greatly benefit because the growing season in Siberia and the northern parts of the Soviet Union might be extended by a month. They're always handicapped by a short growing season by the danger of frost in the fall and the very long time lag in the spring before the crops can germinate. So a longer, say a 25% longer growing season might enable them to double their food production. India, parts of India might, even within one country, parts of India might benefit, other parts might be seriously damaged. And this difference in the effects of different parts of the world will make any kind of worldwide action extremely difficult, particularly a worldwide action to reduce the use of fossil fuels. If we look at the projections of energy use during the next 50 years, the best ones have been made by the International Institute of Applied Systems Analysis, in my opinion, in Vienna. And their estimate is that worldwide use of energy would increase by about a factor of 5 during the next 50 years. And most of this would almost inevitably come from fossil fuels, and particularly for the less developed countries. And this means that the less developed countries are liable to greatly increase their production of carbon dioxide, placing greater emphasis on the short-run benefits of industrialization and increased use of energy than the long-range hazards of the carbon dioxide content. On the other hand, there are only really 3 countries that can really control what happens in the future. Those are the United States, the Soviet Union, and Japan, and China. And the reason for that is that about 75% of the entire coal reserves of the world, and about 60% or more of the entire fossil fuel reserves of the world exist in those 3 countries. Those 3 countries to which nature and God have been so kind. And it's really our decision, and the Chinese decision, and the Soviet decision about what will happen as far as fossil fuel, as far as the major part of the fossil fuel use in the future is concerned. Under the best of circumstances, social and national decisions of this kind could be extremely difficult for political leaders because of the long time horizon and the large uncertainties of the carbon dioxide problem. The dilemma is compounded, however, and this I can't emphasize too strongly, by the fact that decisive action must be taken within the next 2 or 3 decades if profound climatic changes 50 to 70 years in the future are to be avoided. And the reason for this is obvious when you think about it. It takes about 50 years for a new energy source to penetrate the worldwide market. If we're going to make a transition, for example, from fossil fuels to nuclear energy or to solar energy or to wind energy, if you think about that as a major source of energy during the next 50 years from now, you better start right now. And certainly we need a 30-year lead time for any major change in the sources and uses of energy. If we're going to make a transition, for example, from fossil fuels to nuclear energy or to solar energy or to wind energy, if you think about that as a major source of energy during the next 50 years from now, you better start right now. And certainly we need a 30-year lead time for any major change in the sources and uses of energy. Let me conclude by pointing out that the carbon dioxide problem has begun to invade public consciousness at a critical time, when the worldwide industrial civilization is beginning to be shaken to its foundations by the disappearance of inexpensive sources of energy. This is a time when critical choices must be made about future sources and uses of energy, in the realization that all potential energy sources, quite apart from the carbon dioxide problem, have serious social, economic, and environmental liabilities. Government and industry must decide whether to invest vast sums of the order of hundreds and perhaps even thousands of billions of dollars in production of synthetic liquid fuels from coal or oil shale. An equally expensive and widely unpopular alternative is construction of many new nuclear fission plants for generation of electricity or production of secondary fuels. Nuclear fission, as you all know better than I, as a long-term alternative to fossil fuels, depends on development and wide use of nuclear breeder reactors, with the concomitant problems of proliferation of atomic weapons materials. Energy conservation is another, at least partial, alternative. Energy now used in transportation can be conserved by large investments in mass transit, with all that these investments imply in the changed structure of cities. Fundamental decisions must also be made whether to continue present patterns of central station generation of electricity and electrical transmission grids, or to develop local community energy sources. In the bitter competition for dwindling energy resources, the less developed countries without fossil fuel reserves of their own will inevitably be the losers. This means, as I pointed out, most of mankind. Even development assistance from the rich countries to the poor ones is jeopardized because development of the poor countries will inevitably lead both to great increases in their demand for energy and, perhaps even worse, in their ability to compete with the present industrialized countries to acquire fuels in international markets. So there's nothing very cheering about this report on the carbon dioxide problem, but I guess I'm convinced that for the moment at least it's not a very cheerful world. I think I've talked long enough, but I would be very glad to answer questions if that is your custom here. I'm better at answering questions than I am at talking.
If you could go back to 1957 and use the techniques for projecting the effects of an increase in CO2 in the atmosphere, what would they say about 1980 when it risen 6%?
Well, they'd say it was, if we use those techniques in 1957, it would have come out pretty much as it did come out, because by 1957 we were experiencing about a 4% increase in the use of fossil fuels.
Would they have predicted any kind of climate change by now?
No, they would not. Because the natural excursions of climate are of the order of 3 or 4 tenths of a degree centigrade. And I started to talk about Mr. Callender and his explanation of the 70-year-long rise in temperature from 1870 to 1940 as being due to carbon dioxide. That was a very nice hypothesis, except ever since 1940 the temperature's been decreasing. So the climatologists are hard put to it to understand just what has happened.
What rate is carbon dioxide going from the upper oceans to the deep oceans?
How fast does the carbon get into the deep ocean? Is that your question? Not very fast. The best evidence for this is, for the rate at which CO2 gets into the ocean, is something called the Suess effect, which is the decrease in carbon-14 in tree rings from 1850 to 1950, before the first big atomic weapons tests. And those show about a 2% or a little bit more decrease in carbon-14 content. And with any reasonable size of the biosphere, you can't get very much of the total fossil fuel CO2 into the ocean. And we have a pretty good idea of the size of the biosphere. Though the only possibility for more getting into the ocean is something that I certainly should mention, although I don't believe it very likely, and that is that phytoplankton, organisms living in the upper water layers, might die and their bodies descend to the intermediate depths by gravity. This would be a sort of a gravitational pump, pumping carbon into the intermediate depths, not by the circulation of the water, but by a completely different mechanism, where the organic matter is oxidized and carbon dioxide is produced. We know that the intermediate depths contain so much carbon dioxide that if you could just stir the ocean up and overturn it, the atmospheric CO2 would about double. And that may very well have happened at the end of the last ice age, at the time of the climatic optimum. But the other reason why we don't think so much CO2 is getting into the deep sea is that the ocean is stratified, and the communication between the deep waters and the waters near the surface is generally believed to be quite slow.
Don't you have a lot of history on the carbon dioxide content from ice cores from deep down in the Arctic and Arctic?
Yes, that's true. And what that seems to indicate is that the carbon dioxide atmospheric carbon dioxide content was less during the ice age. It's not quite clear what At least I haven't seen any good information on what happened at the end of the Ice Age. Maybe I'm not au courant.
Over the last few hundred years, aren't there pretty good year-by-year samples of the air?
I don't think those are very good, and the reason is that there's so many factors involved in capturing carbon dioxide in ice. At least there have been big uncertainties that have been raised about that.
How much of the CO2 comes from the clearing of land for agricultural purposes and the oxidation of the soil?
What I said was that probably about a third of the total has come that way since 1850. And the reason I say that is that if we look at the total amount of farmland on the Earth, I'm convinced that it's increased by about a factor of 3 since 1850. And a large percentage of that additional farmland must have come from the clearing of forests. The reason I think that farmland has increased by a factor of 3 is that the population has increased by a factor of 3 since 1850. And until after World War II, there was hardly any increase in yields. So it must have been just spreading out on more land. And since 1950, it's still true that in most of the poor countries, where population growth has been very rapid, that they've accommodated themselves, or they've been able to increase their food production to accommodate the growing population by cutting down forests, spreading out on more land. The principal reason why the forests in low latitudes are diminishing is because of the desperate search of poor people for farmland. There are other reasons, but that's the principal one.
And the farm crops don't compensate in terms of use of CO2?
No, because you see, you store wood, you store carbon in wood. You don't store carbon in crops, since you eat them and you put the carbon dioxide right back in the air. You have a big storehouse of carbon in the wood of forest trees, something like 750 gigatons, about considerably more than there is in the atmosphere. But there's essentially no storage in agricultural lands.
Would the prospect of intensive reforestation reduce the CO2 problem, or
Sure. That's been advocated by Freeman Dyson, in fact. In fact, he wants to go one step further. He wants not only to grow a lot more forests, trees, but also to cut down the trees and store them someplace and grow some more. Well, nothing, Freeman Dyson is a very smart guy, and nothing that he says shouldn't be taken seriously. I think myself that this is a second best solution, and if you're going to store carbon in forest trees, the best thing to do is use the forest trees as a source of energy. Substitute wood for fossil fuels.
Does the increase in CO2 cause a possible shift in the pH in the ocean, or is it sufficiently above it?
It certainly will reduce the pH of freshwater lakes and of freshwaters in general. Although the pH of most terrestrial waters seems to be determined by organic processes in the soil and in the water, which tend to lower the pH below that which you'd expect from equilibrium of atmospheric carbon dioxide. In the ocean, you might get a doubling or quadrupling of atmospheric carbon dioxide would result in a significant decrease in pH. Unless you, well, I guess it just would, period, because of the change in equilibrium. I'm sorry to hear that.
Over the near range, then, could that CO2 increase cause a geological shift in the oceans?
Did you ask about the range of change?
No. Could the change in CO2 cause the ecology of the ocean itself to change?
Sure, with pH changes. Have a profound effect on the phytoplankton.
would it increase or decrease the growth of the plankton?
It would change the ecology in the sense that some forms would benefit and others would be damaged. We know, as you know, if you look into these matters, there's a sequence of events in ocean plankton during the year. First things that come are the diatoms, and later the dinoflagellates. And these are due to changes in the minor constituents of the sea. The same kind of thing would happen if the same kind of differences in succession or succession problems would occur with a change in pH. But I wouldn't be able to predict what they would be.
What research is the government doing or supporting to see if a large-scale syn fuel project is really a good idea?
Your question is, what is the government doing to make syn fuels or to not make syn?
No, see if it's really a good idea with respect to the CO2 problem.
Well, one can say that from the point of view of the CO2 problem, it's a bad idea. And the reason is that the CO2 per BTU coming out of synthetic fuels will be about 3 times what it is from natural gas.
But is the government embarking on a project, on a study to see if that in fact is going to cause a massive problem?
Well, they're not doing it quite like that, but the DOE has a major program on study of carbon dioxide, all aspects of the carbon dioxide problem, including its social and economic effects. So they're looking at it in that indirect way, knowing full well that if you go to a full-scale synthetic fuel economy, will rapidly increase the production of CO2.
Did I hear you say that although this carbon dioxide has increased, that the temperature has dropped?
Since 1940, it's dropped about 2 or 3 tenths of a degree centigrade. And the explanation that I think is reasonable is that the climate is noisy, and that if you just kept the carbon dioxide content constant, didn't change it at all, you get, we know over the past several hundred years, you get changes of the order of half a degree to 3/4 of a degree with a time constant of decades. For example, during the 18th century and the beginning of the 19th century, it was very cold. It was very cold in the 17th century. And it was very warm, let's say at the time that Greenland was settled and that Iceland was settled. And along about the 13th century, it became quite cold again. It was called the Little Ice Age. And Hans Brinker and his Silver Skates, for example, are an example of this more recent cold period in Europe.
How long did we have to wait before you could predict a change in climate?
Well, what the conventional wisdom is that we ought to know pretty well within the next 20 years. If the fossil fuel consumption continues to increase exponentially, because we would be using about twice as much fossil fuels in the year 2000 as we are now if that exponential increase continues.
Well, I think perhaps with that question, we ought to thank